going to be recording these lectures and posting them online, which is not an invitation to skip class, okay? I've had students who are like, well, I'll just watch the lecture at home. You'll really miss out on most of the learning because we're going to spend a fair amount of time in class actually working in groups on the board. So we'll learn a concept and then you'll go off and you'll apply it. And I'll walk around and see how you're doing and answer questions. But that's going to be a key part of the learning. And you don't get that if you're just watching the videos at home. But if you prefer not to be writing notes while lecture is going on, or if something happens and you can't come in or you come in late or something, right, the videos are available to augment the course. There's a tentative course outline. Don't pay too much attention to it. Those are the subjects we're going to go over, but the mapping to weeks is always approximate. But it basically follows the textbook. So grading, so you have 7 labs in this course, okay, and that's a quarter of your grade. You'll have weekly homework, possibly quizzes. I'm not going to start off with quizzes, but I will start off with homeworks, and those will bundle up to 20% of your final grade. Midterm for 25, final for 30. So pretty straightforward grading. And ECS course policies page, same as from 120, will show you letter grade assignments and so on. I'll let you read the course policies. It's all pretty straightforward stuff, mostly boilerplate, right? Don't turn in other people's work as your own. Don't hack the computers. Don't deliberately destroy the equipment, and so on and so forth. I generally don't accept late work. Okay, usually when something is due, it gets turned in the beginning of class and then we talk about it. So if you don't turn it in the beginning of class, there's not really a fair way to accept it late, especially since things are recorded. Labs are the one exception. You can turn labs in late because you're required to turn in all 7 lab reports in order to pass the course. You can get a 0 on them, that's okay, but you got to turn them in. You got to actually do all 7 labs to pass. So those I will take late, and we'll talk about grading for those later on. I do want to talk about support services and accommodations. So Clark College is very strongly committed to trying to make sure that everybody has an equitable situation, okay, in being here and trying to learn whatever it is that you're here to learn. So equitable means, for example, there's open seats available. You can sit in any chair you want, right? If you want to sit in the front, you get here early, you can sit in the front. That's equality, right? If you have a class across campus right before this one, you got to run across campus and you can't run very fast, and you get here late and you can only sit in the back row because all the rows up here are filled, but you can't see the screen from the back, right? That's an issue, okay? That's not equitable. So if something is going on where you feel like you're not able to successfully do your best, right, because of some external circumstance, like you can't see the board, or you have difficulty hearing me because you're sitting in the back, or you have trouble concentrating while you're writing and you would like someone to take notes for you, or you don't test well, you have test anxiety, and having extended test time would be helpful, or being able to test in a low distraction environment. If you need some sort of accommodation like that, or you think something like that might apply to you, right, there are a ton of possibilities. So there's this Disability Support Services Office, DSS, and that's what they do, okay? They work with students. If there's a situation that you feel you might benefit from some sort of accommodation, come and talk to me, or go to their website, or call them, or email them, or talk to somebody. Okay, and there's mechanisms here specifically for those kinds of accommodations, and this is for all classes, not just this one, right? So if you're having an issue in some other course, talk to your instructor, talk to me, talk to the DSS office. Does that make sense? All right. So the other thing that I want to go through, and this is probably the only time you'll ever hear me read from a PowerPoint presentation. I don't do PowerPoint usually, but this is the only time I'm going to read from a slide verbatim. I want to read the non-discrimination policy, okay? Because I want to make sure people have heard this and that you understand what it says. So, non-discrimination policy. So Clark College affirms a commitment to freedom from discrimination for all members of the college community. The college expressly prohibits discrimination against any person on the basis of race, color, national origin, disabled veteran status, sex, sexual orientation, age, gender identity, creed, gender expression, Vietnam-era veteran status, religion, marital status, and presence of physical, sensory, or mental disability. The responsibility for and the protection of this commitment extends to students, faculty, administration, staff, contractors, and those who develop or participate in college programs. It encompasses every aspect of employment and every student and community activity. So what's the punchline of all of that? Again, we want your time at Clark, we want your time in the classroom to be spent learning material, struggling with homework questions, working your way through problems on the material, things like that, right? We don't want you to worry about, I really need to go to class today because I don't understand this concept, but so-and-so said such and such, and I'm not comfortable being in that room today, right? That's not acceptable. So if you have an issue that is causing you to be distracted, right? Something that's making it uncomfortable or difficult for you to come to class and concentrate on the material, right? Related to some kind of discrimination or something like that, come and talk to me, talk to one of your other instructors, and we can help you figure out who to talk to, and we can proceed from there. It's not something I've seen very often in STEM classes. Okay, I don't know about other classes. I've only taught STEM here, but there's only been a few times where things have come up, and in those cases, the system worked very well, and it was fairly comfortable to have it resolved. So, if there's something going on, like I say, come and talk to me or talk to another teacher, and we can go from there. Does that make sense? All right. All right, so additional course policies. So the syllabus is kind of general across different offerings of this course. This is the section that relates particularly to this course this quarter. So my name is Nick Macias. I told you my office number, website for available hours. Due dates are listed on Canvas. I'm not always going to remind you when things are due, okay? But all the due dates will be listed on Canvas. You definitely want to refer to Canvas fairly frequently. If there's a homework coming in, it'll tell you what the homework is, it'll tell you when it's due, and so on and so forth. At some point, I may start assigning homework in class. Okay, first two assignments are going to be on Canvas, but at some point while we're going through, we're working on concepts. If there's a concept that we're struggling with, right, we'll do some more work on it, and then I may say, okay, here's a problem to write up for homework, turn it in on Thursday. Okay, and those will generally not get posted on Canvas. So this is one of the reasons you want to be coming to class. I'm doing something new this quarter, which is I'm going to put on specific requirements for how you write up your homework. And in the past, I've kind of said, you know, just turn in your homework and make sure I can follow your work. And what I'm finding is in the final year courses where people are turning in homework, I'm getting some fairly shocking submissions where it's impossible to sort of follow the line of thought, or, you know, simple things like the questions are done out of order. So I'm trying to grade question 7, and it might be, you know, on the first page, it might be at the last page, it might start on the 3rd page and carry on to the 6th page, because I don't know why. So I'm going to put very specific requirements on how I want your homework written up. Okay, and this is good engineering practice, right? And I sat in one of Tina's engineering courses, and she happened to be doing this with her class, and I saw the homework they were turning, and it made me cry. It was so beautiful. So we're gonna play with that, and we'll talk about that in a moment because I've already posted one homework assignment. Quizzes, I'm not doing quizzes up front, but I may do some quizzes at some point. I'll announce it before I start doing that. Okay, I'll say something like, okay, I'm going to do a quiz next week or something. But at some point they may become unannounced. So I'll let you know if that's going to happen. Attendance, I'm not going to take attendance. Well, I may take attendance. I'm not going to count attendance, okay, in your grade. But you got to come to every class as much as possible. Right? If something happens, you got a flat tire, the bridge is jammed up, whatever, and you can't get here, right? Don't panic, right? If you're deathly ill and you need to stay home and rest, don't force yourself to come in. It's not super, life or death like that, and it's not going to count in your grade. But if you make a habit of not coming to class, your grade is going to suffer. Okay, that's just an observed reality from a number of years of teaching this course. If you come to class, 10 minutes late a day, you'll probably drop a letter grade. That's just an observed reality from the past. Because first 10 minutes of class, we go over some stuff that's important, right, or answer questions and so on. And it's really important to be here, like, as much on time as possible. I know it's a big campus, and plan to stay the whole time as much as possible. And if you have concerns about that or you can't make it, you can always shoot me an email and I'll tell you what you're missing. So labs, so there's 7 labs in here. As I said, you're going to do labs in groups. It's probably going to be groups of 4 people because we've got 20-some people in here. So 4 or 3 people. And I'm going to have specific assignments for what I want on, just specific requirements for what I want in your lab reports. So we'll talk about that too when we get to lab 1. Lab reports get written and prepared individually, even though you're working on labs in groups. So you and 2 or 3 other people will actually do the work. You'll build the circuits, take the measurements, record the data, and so on and so forth. But then everyone goes off and writes their own lab report. Okay, and that's really important because we want to make sure you get experience with actually writing technical reports. Tests will be closed book. I'll let you have 2 pages of double-sided notes for exams. So, or 4 single-sided pages if you like, and that's usually plenty. The last note is just keep an eye on Canvas. Once you get graded assignments back, they should be recorded in Canvas. It doesn't hurt to eyeball it and just make sure that everything looks right. Once in a while, there's a hiccup somewhere and you get a 0 on assignment when you actually got 100 on it. And Canvas shows a 0. It's a whole lot easier if you catch that like right away than if at the end of the course you've got a B- instead of an A and you're trying to figure out why. And it's like, well, these 5 things, I know I did these and they're showing up as 0s, and then it's harder to deal with. All right, so that's the course specific stuff. Any questions or concerns on any of that? All right, cool. So how many people here are not currently enrolled for this course? Well, that's not bad. Okay. So yeah, see me at the break. I can add you in. Cool. All right. Well. So we're going to start off with kind of a review of some of the stuff that you did in 120 when you dealt with digital logic and digital circuits. We want to talk about Boolean algebra. We want to talk about number systems, things like that. But let's start off with this idea of digital logic, right? So that's the title of this course. What does digital mean to us? Why isn't it just logic or something? So what does digital mean? Or what might something be if it's not digital?
Like how a computer thinks compared to how we think?
Yeah, like how a computer thinks instead of how we think. That's nice, yeah.
I think of it as not analog.
There you go, not analog, right? So what does analog mean?
It's just a stream of electricity, let's say.
Mm-hmm.
And so rather than just having the full stream as like a full graph, you take chunks of it, and that is a representation of it as digital.
Okay, perfect. So let's play with that. You listen to music, right? Either through speakers or headphones or car radio or whatever, right? How does music work? How do we hear music when it's like we turn the radio over here and our brain hears a song, right? So what's the transmission mechanism? How is that music somehow getting into our head when the speaker's over there in the corner?
Sound waves.
Sound waves. What are sound waves?
They're analog waves that the speaker's pushing in
Okay.
the car to push air.
Air, okay, so air is the transmission, right? So this is kind of freaky. If you try to explain this to like an alien, they'd think you were crazy. But this is how it actually works, right? A speaker over there is moving, so the cone of the speaker moves back and forth, and it's pushing air when it moves forward, and it's pulling air when it moves back. And that air that gets pushed travels across the room, and it hits my eardrum, and it pushes my eardrum in the same way that the cone of that speaker moved, right? And so my eardrum is mimicking what that speaker is doing. Well, that speaker is moving in such a way that my brain will hear notes or voices or whatever was being sent through that speaker. And we can represent that with some kind of graph. We can say time. Well, we're engineers, right? So we usually talk about voltage. That speaker is an electrical component, and depending on how much voltage you put through the two connection points on the back of it, that controls how much the cone is moving. So we can actually think of this movement of the cone as sort of a time versus voltage type of situation. And as we move forward in time, this voltage might do something like this. Right, so it goes up and down, positive and negative. And if we looked at the actual pressure of the air in front of the cone, it would do something with a similar shape to this. And if we looked at the electrical signals coming from my ear mechanism into my brain, it might look something similar to this, right? So this is an analog waveform, right? It's analog in the sense that that it's smooth, right? It doesn't suddenly jump from here down to here. It slowly changes and decreases until it gets down to here. And it doesn't jump from here up to here, it comes down here and it turns around and goes back up. It's nice and smooth, or continuous, if we wanted to use a mathematical term. It's a continuous waveform. Okay, so that's analog. And to some degree, the universe is analog. To the degree that we sort of observe it at our scale, things seem to move like this, right? If I drop this, it doesn't suddenly move from here to here. It slowly transitions through a bunch of points in between. You can't see that on camera. There you go. So this is kind of how the universe works, but it's a little hard to work with. It doesn't lend itself very well to working inside a computer. So we can approximate this kind of analog waveform in a way that lets us put it inside a computer and then do things like write programs or build circuits to deal with this. And so we do something called digitizing. And how does digitizing work? Well, we think of this as no longer moving smoothly. We think of it as moving through a series of discrete values, maybe like this. So we break it into these little staircases. And now we can represent this waveform by assigning numbers to each of these steps. So maybe this is 0, and maybe this is 1 and 2. And let's say 3, and 4 and -1 and so on. And now we can say, so what did this waveform do? Well, it started off at 0, and then it went to 1, and then 2, and then 1, and 0, and -1. And we can record at each point in time, we can break time up into certain steps, and at each point in time we can say what was the value of this waveform. And it's a bunch of integers. Well, computers like integers. Okay, we can store integers really easily in computers. And so we digitize this into this digital waveform. Okay, so this is what CDs do. A CD, so a CD is a representation of basically sound waves that's been broken into these little discrete steps. So we go boom, 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 boom through these fixed points. Anybody here ever play with vinyl records? So a vinyl record, if you look at it, it's got little tracks cut into the plastic that actually look like this, right? They actually wiggle back and forth, and they're a representation in a physical medium of what this waveform is. And when you play a record, there's a little needle that sits in there, and as the record spins, the needle moves in the same way that this waveform looks. That's changed into a voltage, and that's driven to a speaker. And so your speaker is mimicking this. That's an analog representation of sound. CD is a digital representation. Anytime you have a file on your computer, a WAV file, an MP3, whatever, that's a digital representation of a sound wave. So in this course, we're only interested in these digital realms. Okay, we're not going to do anything analog. Analog, that's when you're doing KVL, KCL. Anybody here want to do KVL, KCL this quarter? No, okay, so we'll stay away from analog. We're just going to do digital. And digital is a whole lot easier in some ways to work with. Because at some level, you know, we've only got a few values to worry about, 0, 1, 2, -1, and so on. But it gets even better than that. At the lowest level, in a digital world, we only care about 2 values, 0 and 1. And everything is either a 0 or a 1. And if we want more values, if we want to have 8 different voltage levels that we can represent, we can't represent that with just a 0 or 1, but we can use a collection of 0s and 1s, right? So you probably remember this from 120. I can make a pattern of 3 of these 0 or 1s, these binary digits or bits, and I can just decide arbitrarily this is a 0, 1, 2, 3, 4, 5, 6, and 7. And now I can represent 8 different values, still just using 1s and 0s. So we're going to do a lot of that this quarter. And 1s and 0s are nice because it's fairly straightforward to build circuits that can deal with 1s and 0s. So how do we represent 1s or 0s in digital logic? You did this in 120.
On or off.
On or off, right? Pretty much anything binary will work. So we can do on and off. We can do yes and no. We can do true and false. That's where Boolean logic came from in the 1850s, was studying philosophical questions about reasoning and truth and falsehoods. Anybody here have a ballpoint pen with a clicker on the top? You like click and the point comes out, and you click again, the point goes in, right? That's a binary system. You could build a computer out of those. Be a fun computer. Be a noisy computer. So we'll usually stick to this convention where we look at voltages, and we're only going to deal with 2 voltages, 5 volts and 0 volts, or ground. And usually we're going to say if something is at 5 volts, that's a logic 1, true, on, yes, whatever. If it's at 0 volts or ground, that's a logic 0, that's off, false, no. So our circuits get a little simpler to analyze because every point in the circuit is supposed to be either 0 volts or 5 volts. So all the stuff we had to do in 120 to analyze circuits, that all becomes a little more simple in some ways. All right, so this is the realm we're in, right? This digital realm. Boolean, two values on or off, 1 or 0. So this is also a Boolean system because we've got just zeros or ones. All right, so we need to do things like this, right? We need to live in a world that has more than just zeros and ones. We need to deal with numbers or real numbers like pi or the square root of 2 or 6.5 or pictures or movies or pages of text, right? So we need a way to represent these other things using combinations of zeros and ones. We need some sort of coding. And the first coding we want to look at is coding numbers. So we want to take numbers and represent them with ones and zeros. And we just did that on the other page, and you've done this before, but let's dig into it further. So that's the number 0, right? So why is that the number 0? Because we decided it is. I could say that this is the number 0. And I could build my whole world around the idea that this is how I represent the number 0. Nothing wrong with that. You know what? We've decided this is the symbol for 0, but there's no reason that's the symbol for 0. That's just a convention. I might decide this is the symbol for 0, and this is the symbol for 1. Can I still build my civilization? Absolutely. So these are just conventions. But there's a reason why this convention works really well. And it's a reason that we actually learned back in grade school. It's something called weighted positional notation. All right, so I'm going to write something you've never seen before. Has anybody here ever seen this number before? Probably not. Is there anybody who does not understand what this thing I just wrote is, though, as a number? I mean, if I asked you to multiply it by 2 or add 1 to it, you'd be able to do that, right? Even though you've never seen this particular combination of symbols before, right? Because we don't make random assignments and say this is the number 5, this is the number 6. We have a method for representing numbers by writing these symbols next to each other. And the method is, this is the ones place, or the 10 to the 0 place. 10 to the 0 is just a fancy way to say 1. This is the tens place, which we can write 10 to the first. This is the hundreds place, which is 10 to the second. This is the thousandth place, which is 10 to the third, and so on. And so this number here means 9 times 1,000, plus 7 times 100, plus 6 times 10, plus 3 times 1. And we all understand that, and we agree that that's what this set of symbols means. So we're going to do exactly the same thing in binary, right? We're going to write down a binary number, so this is decimal. So in binary, we can write something like 100101. And what does it mean? Well, this is 2 to the 0, 2 to the 1, 2 squared, 2 cubed, 2 to the 4th, 2 to the 5th. So this is 1 times 2 to the 0, 0 times 2 to the 1st, and so on. And we multiply those out. This is 1, 0, 4, 0, 0, 32. And we add them up, and we get 37. And so anybody who understands binary numbers will look at this and say, yeah, this is the number 37 decimal. And that's really convenient because with decimal numbers, as humans, we know how to do things like multiply this number by 2. or add something to this number. To add two decimal numbers together, you add column by column. And if you get a carry, you bring the carry over to the top of the next column and you add that through, right? We can do the same thing in binary. And we can multiply in binary, and we can subtract, and we can divide in binary. And it works exactly the same as what we're used to. And this is what computers do, right? When they add two numbers together, they basically add these columns, and if there's a carry, they put it in the next column, and they add those, and so on. But that only works because in binary, we're using this weighted positional notation. So this is almost always the way we're going to represent integers. Okay, it's a sum of the weights of each position multiplied by this digit. Okay, so here's the first possibly new thing, or possibly the first new thing. Converting from binary to decimal, straightforward, right? Just add up the powers of 2. Converting in the other direction is a little trickier. So let's pick a number. I don't know. Let's do 62. I don't want to do 62. Let's do 59. And we want to convert 59 to binary. So we want to find the ones and zeros that add up to that. Okay, so you can do this by trial and error. You can start subtracting off powers of 2, and your biggest power is 32, and so on and so forth. But there's a systematic way to do this also. And I want to make sure you've seen the systematic way, because it's not always something we know. So here's how I systematically convert 59 to binary. So I'm going to take 59 divided by 2. I'm going to write it down as some integer and some remainder. Okay, so 59 divided by 2 is 29 with 1 left over, remainder of 1. Okay, I'm going to take this 29 divided by 2, and that's going to be 15 with a remainder of 1. Sorry, 14. I was getting worried. All right, I'm going to bring the 14 over, and that's 7 with a remainder of 0. I'm just going to keep doing this. So 1 divided by 2 is what? It's 1/2. Well, what's it as an integer? It's 0 with a remainder of 1. That one's potentially tricky. Okay, and how about 0 divided by 2? That's 0 with a remainder of 0. And at this point, if I keep going, I'm going to keep getting the same answer. Okay, so once you get down to 0, remainder 0, you're finished. So now, we're going to grab all of our remainders. And I'm just going to write them down. That should be 59 in binary. And if I had kept going, I would just be getting more zeros in the beginning here. And that's okay, that doesn't change the value. It's like writing a bunch of zeros in front of a decimal number. Doesn't change the value, right? So if you go too far, you'll just end up with some zeros here on the left, not a problem. So this is 59 in binary. And it's 1 and 2 is 3, plus 16 is 19, plus, sorry, 1, 2 is 3, and 8 is 11, plus 16 is 27, plus 32 is 59. All right, so have you seen this before? Some have, some haven't. Okay, so that's the systematic way to convert to binary. So terminology. So these are bits, right? Binary digits. That's what a 1 or a 0 is. So we call them bits. This bit here on the right, we can call it the bit on the right, but that's a little biased because sometimes we write our numbers with this bit over here on the left, right? So an unambiguous way to identify this bit is the LSB, the least significant bit. And the bit over here on the left, we can call that the MSB. That's the most significant bit. And a way to remember that, why is this least significant? Because if this were to change from a 1 to a 0, what happens to the value of the whole number? Does it change a lot or a little? Changes by 1 or minus 1. But if this number here on the left, this is the 32's place, if that changes, the value of your number changes quite a bit. Right? In fact, that's the most significant change you can make to your number, is changing that. So that's the most significant bit, that's the least significant bit. Usually it's a little b for bit. So we'll use MSB and LSB to refer to the ends of this. And I'll usually take a break about an hour in. We'll take like a 5-minute break and then come back for a second half. All right, so you live in binary land, and you and your friends are all binary, and someone wants your phone number, and so you say, yeah, here's my phone number, it's, right, and you're trying to read this to them, so it's 1001110111100, right, and they're like, wait, was that a 1 or a 0, right? Very inconvenient for people to deal with binary. Great for computers, right? This is what computers actually ingest, is 1s and 0s. But for people, this is kind of a pain. So we don't usually throw around long strings of binary numbers. So we can do things like, for example, break this into groups of 3 bits. And convert each of those 3-bit groups into a single number. So 101, if we convert that to decimal, that's a 1 plus a 4, that's a 5. 101 is 5, 011 is 3, that's a 6, 3, 7, 4. And now we can say my number is 4736355, and I can say that's an octal, or base 8. And that's just better for humans. And sometimes if we want to represent that something is in base 8, we just put a little subscript of 8 next to it. And if we want to represent that something is in binary, we could put a little subscript of 2 next to it. Because if you're doing a problem in digital logic and you see this, we don't know what that is. That could be the binary number 5, it could be the decimal number 101. There's an ambiguity. So if I put a decimal point here, or a little subscript 10, or maybe sometimes a D, there's different notations, right? But somehow I could indicate this is a decimal number, or I could say that's base 2, it's a binary number. And the book has some different representations, and the other sources have different representations, and if you're not sure what the representation is, go ahead and ask. Yeah.
What's the most preferred standard?
I don't know, but for me, if I'm in binary, I usually do a subscript of 2. If I'm in decimal, I usually put a period. And for octal, subscript of 8. But in programming languages, there's different standards. For example, in a programming language, if I wanted this number in octal, I would put a 0 in front of it. And in a language like C or Java, if there's a 0 in the beginning of an integer, it assumes that's an octal number. Just works out that way. Yeah?
I'm curious, would you do like a 0 then space, or just 0?
Just a 0 followed by that. Which should just be, you know, this number in decimal, but it's just a convention in C that represents an octal. Well, another thing we can do so there's a 16-bit number. Probably the most common way to represent this for human ingestion is to break it into groups of 4. and write down each of these 4 bits as an integer. So 0001 is the integer 1, 0101 is the integer 5, 0011 is the integer 3, 1100, that's actually the integer 12. But again, we've got a potential confusion here. If I write down the number 31251, how do I know that I meant this 16-bit number 31251 as opposed to a 20-bit number 31251? So we don't want to write down something that has 2 digits to it. So we come up with a different way to write the numbers 10 through 15. So the numbers 0 through 9 we just write as 0 through 9, but 10 through 15 we write as A through F. So instead of a 12 here, I would write down a C, and I would say this number is 3C51. And you can put a little 16 as a subscript to say this is base 16 or hexadecimal. Or the most common way here is to put a little subscript X, as in hex. In programming languages, if you write 0x3c51, that tells the compiler this hexadecimal number, so base 16. Just because you can't put subscripts in programs usually. And sometimes you'll see this with an H at the end to mean hex. Again, different notations. So those are the main ways that we're going to represent numbers, either straight decimal, which we understand, binary, which is just the ones and zeros, octal, where we break it into groups of 3, or hexadecimal, where we break it into groups of 4, and use these letters for numbers 10 through 15. Good with that? Okay. All right, let's go ahead and, yeah, go ahead.
Well, I noticed that every time that you converted from binary, you converted back to decimal and then to hexadecimal or octal. Is there a way to just convert directly to it, or is it just too complicated?
Ask that again.
So when you converted from binary to hexadecimal, you went from binary to decimal.
Like going to a 12 and then to C?
Yeah.
Yeah.
Is there a way to just convert directly to it? Or I guess the 12 is just a C.
Yeah, so when you see this, you actually think C and you write down a C. But at first you think 12 and then you look it up or remember it.
Right.
You could also take this number and convert it to decimal, right, by adding up the powers of 2. And then you could do this trick, dividing by 16, right, to convert it to hex, and that'll get you the same thing. But it's a lot more work. It's a whole lot easier to just do that. And if you want to convert this to decimal, you can convert it to binary and add up powers of 2, but this is also weighted positional notation, but it's with powers of 16. So this is the 16 to the 0 place, 16 to the 1, 16 squared, 16 cubed, just like powers of 10 in decimal, but powers of 16. So you can go from here directly to decimal without having to go through binary. Keep in mind, in reality, right, computers do all this for us. We don't usually do this, but sometimes you need to do it, and Google will do it for you too, but don't use Google. It's good to be able to do this yourself. All right, so let's do like a 5-minute break. Come back here at 12:55, and I want to do a quick rehash of some analog circuit work from 120 because I posted a homework question. Then I want to talk about homework requirements, and then we'll continue on with Boolean things.